So, welcome back. This is the last session in the BIM Awards, Open BIM Awards Finalists 2025. The last two categories are student research and professional research. So, without further ado, I'll hand over to the first presenter, which is the School of Software, China.
Good afternoon, ladies and gentlemen. It's my honor to be here. Thank you for this wonderful opportunity. My name is Yudong Liu, and this is my colleague, Han Huang. We're both students from School of Software, Tsinghua University. We're very excited to share with you the vision of BIMNet, using openBIM as data foundation and take a step towards AI plus AEC. To better explain the vision, let's first look at how AI is changing our life. Around us, AI applications are everywhere, from face recognition to autonomous driving, from virtual reality to robotics. Behind these applications are core technologies: image recognition in two-dimensional field and scene understanding in three-dimensional field. But no matter in which field, one thing is always important: data. Modern AI is data hungry. Without open and high-quality data sets, none of these tasks would exist. In fact, both 2D and 3D AI breakthroughs stand on the foundation of open datasets. For example, ImageNet in 2D and ScanNet in 3D. Open data not only fuels innovation, but also provides us with key benefits. They provide essential standards, enable AI training, lower costs for data annotation, and also promotes research collaborations within the community. But what about our own field, the architecture, engineering, and construction AEC industry? In AEC, as-built BIM modeling is critical for many applications: building renovation, digital twin city, and facility maintenance. One of the core technology behind them is scan-to-BIM, now increasingly enhanced by AI. But here comes a problem. Unlike 2D and 3D AI, scan-to-BIM still lacks large-scale, domain-specific datasets to support its development. So, this is exactly the gap our work aims to fill. We introduced BIMNet, an open-source large-scale dataset for scan-to-BIM. So what is scan-to-BIM? It is a technology that models as-built environments. It takes raw point cloud as input and output as-built BIMs, which can be used for various applications. Nowadays, scan-to-BIM is increasingly starting to embrace AI. But here, we have still lack of large-scale domain-specific datasets, multi-dimensional accurate benchmark, and finally, we lack a standard workflow for AI-based methods. In short, AI is here, but scan-to-BIM is missing the foundation it needs. These three issues create many obstacles for researchers in the field. For example, without a large-scale dataset, how can I train my AI-based algorithms effectively? Without a reliable benchmark, how can I evaluate whether my algorithm is good enough? And also, without a standard workflow, how can I even apply AI to my research? These unanswered questions show the urgent need for a new solution. To answer this question, we present BIMNet with openBIM as foundation. Leveraging the open source, technically mature, and standardized features of openBIM, BIMNet aims at addressing these three challenges with three IFC-based designs. First, an IFC-based domain-specific datasets with real-world point cloud and also manually modeled IFC data. Second, an IFC-based multi-dimensional benchmark covering both geometric and topological evaluation for scan-to-BIM. And third, an IFC-based scan-to-BIM workflow, integrating dataset, benchmark, and also multiple plug-in AI-based algorithms for scan-to-BIM. In short, BIMNet provides the missing foundation for AI-enhanced scan-to-BIM. Now, let's start with our three key designs. Our first key design is an IFC-based domain-specific dataset. We first manually modeled raw point clouds into ground truth IFC models. Then, we designed an IFC-based semantic annotation system, refining point cloud labels into IFC categories. As for the details of label design, we select appropriate point cloud labels based on point distribution and IFC. In this way, BIMNet bridges point clouds and IFC components with precise semantic alignment. To be more specific, BIMNet covers the most essential building elements for scan-to-BIM tasks, all aligned with IFC standard. As a result, the IFC-based point cloud semantic refinement improves annotation accuracy, and the IFC-based label design improves the performance of AI algorithms. The second design is an IFC-based multi-dimensional benchmark. We compare the ground truth IFC model from BIMNet with the user IFC model generated by user scan-to-BIM algorithms. This usually reveals reconstruction issues within the user IFC model. For instance, some wrong with the wall thickness, also the tilt and shift walls. Here, the problems become how to analyze these issues visually and how to measure these issues quantitatively. This is a very important thing because with this kind of technology, we can locate issues visually to improve our algorithms, and we can also compare different algorithms with unified metric. Here is our design. For our benchmark, we first get the representation and placement information from IFC models. Then, we develop geometric benchmark based on 3D intersection over union to evaluate the accuracy of reconstructed shapes. We also develop a topological benchmark based on normalized graph edit distance. Graph edit distance is a kind of technology to measure the difference between two graphs. The topological metric is aimed at evaluating the correctness of spatial relationships. Then, these metric designs are implemented with IFC OpenShell, Python, and also Open3D for measurement and visualization. As you can see, our geometric benchmark are sensitive to thickness, also the tilt and shift of wall components. And our topological benchmark are able to find wrong space connectivity and wrong enclosed spaces. Our third key design is an IFC-based scan-to-BIM workflow. First, we have our IFC-based dataset. Our dataset serves as the foundation for training plug-in AI-based algorithms. Our benchmark evaluates the performance of the algorithms. Once the algorithm is trained and validated, it is ready to be deployed online. Our workflow finally takes real-world scans as input and output as built BIMs for various applications. Next, let's go through the 3 key outcomes corresponding to our 3 key designs. The first outcome is we publicly release BIMNet. It is an openBIM-based large-scale scan-to-BIM dataset, spanning more than 8,000 square meters and encompassing more than 300 rooms. Here are some interactive demos for our datasets. Each data example includes real-world point clouds, IFC-based semantic point cloud, and also dedicated BIM models to support training and evaluation at all stages of AI-based scan-to-BIM. The second outcome is we propose an IFC-based multi-dimensional benchmark. As for the IFC-based geometric benchmark, through real-world and scale-up stress testing, it is proved that our geometric benchmark significantly increased the issue detection rate and also the evaluation efficiency. The proposed topological metric also fills the gap of the underexplored scan-to-BIM topological metric with IFC-based design. Our third outcome is an IFC-based scan-to-BIM workflow. Today, many of our colleagues talk about combining AI and AEC through large language models. However, in our research, we want to offer a different perspective, connecting advances in computer vision with AEC, especially highlighting the importance of AI-based point cloud semantic segmentations in scan-to-BIM. At the stage of semantic segmentations, as you can see, we're able to train and validate up-to-date AI-based algorithms with BIMNet. While at the stage of the component reconstruction, we can also analyze and evaluate scan-to-BIM algorithms with BIMNet workflow. We want to emphasize why openBIM is the key foundation of BIMNet. openBIM provides us with mature and widely adopted BIM standards, which are suitable for AI training. The open nature of openBIM has made it easy for us to access geometric and semantics of IFC. We can also build open source community around BIMNet. Meanwhile, we came to realize the critical role of openBIM as the bridge between AEC and AI. This will be further introduced. Thanks to openBIM, with all the outcomes, we built open source community around BIMNet. Currently, we're supporting more than 20 organizations in training and developing their AI plus AEC tasks. Our paper is published in Automation in Construction, and also on the Chinese internet, our outreach article gained wide attention, showing strong public interest and impact. Finally, let's take a look at the vision and potential of BIMNet through examples from our community. Our community brings together researchers from many different fields, like robotics and computer vision. They are now combining openBIM with BIMNet and with their own expertise to tackle an even broader set of AI applications, which I found really exciting. As you can see, beyond supporting scan-to-BIM itself, collaborators apply BIMNet to new AI plus AEC tasks, such as embodied AI and also domain adaptive segmentations. We feel truly grateful that BIMNet can play even a tiny role as data bridge on our shared path towards AI plus AEC. We believe this is just the beginning. With the support of the community and the power of openBIM, we're taking a meaningful step toward AI plus AEC. We sincerely welcome you to visit and download BIMNet. We have our links here and everything is open source. That's all. Thank you for your attention and thank you for this wonderful opportunity.
Many thanks. So the next presenter in this category is LeapThought Asia with Singapore University of Technology and Design.
Good afternoon, everyone. My name is Vanessa, and today presenting with me are my teammates Jiakang and Jolene, and we are from the Singapore University of Technology and Design. We will be presenting our final year project in SUTD, CarbonSmart, an embodied carbon calculator with an AI material filler. This is done in collaboration with LeapThought and the university. First of all, we'd like to explain more about the project. Is that it's a final year undergrad interdisciplinary project done by architecture students as well as computer science students, together with our faculty as well as LeapThought, who was our industry partner throughout our year-long project. We would like to acknowledge SUTD as well as LeapThought for making this possible today, and also extend our acknowledgement to our rest of our teammates back in Singapore. With that, we'll start off with a short introduction of CarbonSmart with the video.
Climate change is no longer a distant threat. As the global population grows, carbon emissions will keep rising. The built environment industry is responsible for 40% of global CO2 emissions. Unlike operational carbon, embodied carbon is locked in once construction begins. That's why managing embodied carbon at the design stage is more urgent than ever. But today, carbon checks are manual, tedious, and slow. And that's why sustainability is often an afterthought, until now. I'm CarbonSmart, the smart way to reduce embodied carbon quickly, accurately, and sustainably. Let me show you how I work. Let's create your first project. Upload your IFC file. I'll scan and identify all elements. I'll check your materials against my database. Don't worry, I'll catch any mistakes. Fix what you can. I'll take care of anything left behind. All set? Sit tight. I'm calculating the values. That's it. Here are your results. Not sure about everything? I've got it covered. Got a new iteration? Drop it in. Let's see what's changed. All done? I've got your results ready for export. Perfect for your documentation or reports.
Our vision for CarbonSmart is making embodied carbon visible, early, and easily actionable through open data standards, thereby empowering the AEC industry for smarter decision-making as well as a sustainable future. So how did we come about with our project in the first place? We found that embodied carbon is often overlooked and not considered early. With the overall 40% contribution by the AEC industry towards global carbon emissions, it is important for us to reduce carbon emissions to save our environment as well as its downstream impacts. Traditionally, operational carbon has been at the forefront of industry efforts. However, we believe that there needs to be a shift to focus in embodied carbon, as embodied carbon is set in stone and there's a shorter time frame for embodied carbon to be tackled. From our interviews and surveys with different companies in the AEC industry in Singapore, we found that the embodied carbon documentation process is currently a very manual and tedious one. This means that a lot of manual data processing is needed from the different stakeholders in order to arrive at the final embodied carbon calculation, which often takes up 2 weeks. This brings us to our problem statement. How can we streamline processes between the AEC stakeholders during the pre-construction design phase to effectively reduce embodied carbon of buildings? A bit more context about our project is that we're based in Singapore, which is one of the first few countries to have mandatory BIM submissions along with openBIM data standards. And that helps our project aligns with the national standards and goals, such as using openBIM during integrated planning and design, as well as looking towards a sustainable urban system towards decarbonization efforts. Using this baseline of Singapore, we envision that CarbonSmart can be sort of a pilot testing in Singapore before scaling up globally, as well as since that Singapore has already used openBIM in their national compliance checks, that embodied carbon can be part of that natural workflow as well. We also envision that CarbonSmart can help set a global blueprint to do decarbonization through openBIM. And all of this was kept in mind to prospectively integrate into LeapThought's platform of Fulcrum HQ with the launch of ConnectX, which is Singapore's mandatory openBIM regulatory submission platform. So from our design process, we understood that multiple AC stakeholders use different authoring tools and different file formats. And when embodied carbon calculations are involved, this often takes a lot of processing because of the different file formats and data requirements needed. And after long weeks of processing this data, it ends up in a very technically detailed report for documentation, but it's often detached from the BIM model as a lot of processing needs to be done. Furthermore, there's no clear actionable results for stakeholders to reduce embodied carbon. It is simply a documentation of embodied carbon of the building. However, with openBIM, we envision that with an IC file, which is a centralized single source of truth, different stakeholders can still use their native authoring tools and then submit it into CarbonSmart. CarbonSmart will then automatically detect all the information embedded in the IFC file and automatically generate clear actionable results and visualizations on the dashboard. With detailed breakdowns and comparisons towards current green building standards, we hope that there will be clear actionable results for stakeholders. And with an easy and quick upload, there's many design iterations and options can be quickly reviewed and compared to it.
And here is a quick overview of the system architecture itself that is tying our working prototype together. So for the front end, we have a simple React, lightweight React front end for uploads as well as visuals. And this will be talking to our fast API service that queues and processes our IFC files based on, and we also implement IFC OpenShell as well. This will give us results, embodied carbon results, charts, as well as reports. And despite every authoring service like Revit having their own set of plugins, openBIM or IFC itself has allowed for us to have one neutral format to ensure not only a smooth workflow, but also less vendor lock-in, as well as a larger market that we can serve, because teams would not have to change like the authoring tools that they use. And this also aligns with the industry recognized, the Singapore Industry Transformation Map, as well as recognized standards that was mentioned before, so that teams can actually integrate this into their existing delivery purposes while focusing and advancing digital and sustainability goals that they have. So with the LeapThought's guidance on with their experience for having developed their own rule checking system, we actually came out with our own rule interpretation on how our calculator extracts data as well as how it calculates embodied carbon. So custom rules were developed for each IFC entity, where through multiple iterations of our rule interpretation document, these rules itself could be applied uniformly across multiple IFC models, ensuring a repeatable and accurate EC calculation regardless of project complexity. openBIM as well as IFC has also allowed for consistent material schema traversal and classification into the specific IFC entities. And this makes actually the workflow to calculate the embodied carbon very easy as well as consistent. And our core product itself actually produces and manages to calculate and produce trusted embodied carbon output with error handling. But the AI component that we have makes it smarter. So what happens is that using a sentence transformer model, if your model somehow has undefined or mistyped materials, we will learn from the model itself will learn from past information to select the best fit for the material. And despite our system actually working well without AI, this AI material filler will actually result in fewer defaults, less rework, as well as more accurate EC calculations.
And with that, we see CarbonSmart being sustainable for both business and environments. So one key impact of CarbonSmart will be to increase opportunities for reduced carbon intervention at early stages of design. This eventually saves manpower costs for design changes along the way. And additionally, we help to keep the history of file uploads, assisting the users in design iterations, mitigating potential errors in every process. This results in a lower risk of communication breakdown with greater transparency. And more importantly, we help to reduce the time taken from 2 weeks worth of work to 5 minutes, where we give you quick and fast, accurate calculations with visual feedback and dynamic results. And so, in the long run, what CarbonSmart aims to do is to enable a greater understanding of embodied carbon with design decisions made in the AEC industry. We help to benchmark against green standard and compliances, giving quick and accurate visual changes with the material substitutions, eventually revolutionizing design decisions to be more sustainable. Thus, CarbonSmart, to reiterate our mission, is to make embodied carbon visible, early, and actionable through open standards, as well as to empower the AEC industry for smart and sustainable decision-making in the future. And so once again, CarbonSmart would not have been possible without the foundation that LeapThought has laid out for us. To give some context on this foundation, CarbonSmart was developed not as a standalone tool, but as part of a much larger vision for Singapore's digital built environment. This vision is powered by LeapThought's platform, Fulcrum HQ, which forms the backbone of Singapore's next-generation regulatory system under CornetX. Fulcrum HQ is a cutting-edge cloud-first platform, transforming how enterprise knowledge, productivity, and regulatory data are managed. It underpins the CornetX collaboration platform, which is central to Singapore's industry transformation map. By shifting regulatory submissions from isolated documents to coordinated model-based submissions, CornetX leverages openBIM for seamless collaboration across disciplines and agencies. And this is how CarbonSmart can eventually plug in as part of a sustainability compliance check. That means embodied carbon national submission framework. A key feature of Fulcrum HQ is its automated model checker, which aligns with Singapore's vision of regulatory efficiency through openBIM and automation. Just as Fulcrum HQ applies advanced algorithms to validate design rules, CarbonSmart applies its own calculation rules to assess embodied carbon within IFC models. Both share the same foundation, using openBIM to ensure accuracy, repeatability, and industry-wide applicability. These are just examples of the type of automated regulatory checks already being handled through Fulcrum HQ. The value here is that once data is embedded into the BIM model, it can be checked automatically, consistently, and transparently. And this is exactly the philosophy that CarbonSmart builds upon. When embodied carbon is embedded into the same openBIM model, it can also be automatically checked, benchmarked, and improved. In this way, CarbonSmart is not just an academic prototype, but a potential extension of the same ecosystem that is already transforming how Singapore builds. And with that, we would like to thank again to LeapThought and SUTD for supporting us throughout the whole process, as well as to buildingSMART and the jury for allowing us here to present our project to you. Thank you.
Thank you. And the final presenter in this category is the Military Institute of Engineering.
Good afternoon. My name is Rafael Tranto, and the work I will present today is called openBIM-FM, Artifact Directional Solution for Efficient Asset Management. This is the result of my master's research at the Military Institute of Engineering by supervision of the Professor Giuseppe Miceli Jr. The motivation for this research comes from a very common situation that happens in almost every construction project. During the design and the construction phase, architects and engineers use many different software tools, and which one generates its own file format. Moreover, these professionals usually are not concerned about the reliability or the quality of the information to be transferred to the subsequent phases. As a consequence, when we need to start a handover, the facility teams do not receive a useful package of information. The information is usually disorganized and disconnected in several file formats as PDFs, IFC files, or other formats. And as a result, we don't see the benefits of BIM to support facility management as we imagine when are using the BIM methodology. During this research, we identified the three main causes that makes BIM hard to be useful for facility management. We have interoperability problems, existence and accuracy of the information delivered at the as-built model, and the data loss when we are transfer the files. I believe everyone here agrees that for the first and for the third reason, openBIM has great potential to minimize these issues. For the second one, we will soon see how we can deal with it. So our objective here is to ensure that the final model, our as-built model, has the necessary information to support the operational phase with reliable information. For that, a solution was developed that we can break it down in 4 components. The first component is a compendium of the most common information requirements to support the operational phase, to help the owners to develop their asset information requirements. The second component is a web platform designed to organize, centralize, and verify the asset information during the building phase. The third component is the REST APIs that will be responsible to transfer the information from website database to other softwares. And the third component is a Blender add-on that will be responsible for send and receive the information from the web platform database. For component number 1, we analyzed the 3 main sources to develop this list of the most common information. And why does it is important? Because we understand that the one reason for the model are not prepared to support the operational phase is because the owners don't know how to develop their asset information requirement. Although the ISO 19650 stands that this is the obligation of the owner to develop it, in practice, they don't know how to do it. So we are proposing a list of the most common to help to start their process. It's not a final list. It's just a list to start the process to help. Using this information requirement, we develop a web platform. And why a web platform? Because we understand this is the easier way to manage the informations. Because here we don't need any BIM software or non-BIM software. Just a simple laptop or a smartphone, we can access the information, edit it, and verify the information during the building process. The third component, the REST API, is the most important part of the solution because it will give us the necessary interoperability to transfer, use, and reuse these informations in third-party platforms as Revit, Blender, Excel, Power BI, or in a future internal automations. But here there's a problem. The API doesn't have the necessary mechanism to give us the security of the database. Everyone who have the assets of the API can visualize or change the information. To solve that, a token security mechanism was implemented. We used the JSON Web Token, and when the user wants to make a request for the API, he needs to send his personal token. If the user has the necessary credentials, the API will give him a JSON response, another open format, and will allow the user to see or perform a specific action. If the user doesn't know the necessary credential, the API denies to access or perform a specific action as edit or delete information. And the fourth component, the Blender add-on, has three text input fields. The first one to inform the IFC class, that I want to create the registers in the web platform. The second is the API URL address and the user token, and 5 action buttons. For the first one, from Blender, I can create a register in the web platform. In the second one, I can receive the information in Blender from the database. The third one is the opposite flow. I can edit the information in Blender and send it to the web platform. Now, here we have a bidirectional flow. And the last two options is for mass operations. So I can create all the registers of a specific class in the web platform or receive all the information updated from the web platform. In our case study, I used a student dormitory, the IME Annex building, and it has hundreds of assets, but we will focus on an HVAC system, more specifically on air conditioner system that we are seeing. When we start to analyze the model in this sidebar, in the side menu, we can see that we don't have the necessary information to start the operational phase. So we started the process. Here, we are informing the IFC class, the destination URL, and the user token. After that, we select the option book create. After that, all the registers of this specific class was created in the web platform, as it was in the IFC file. So here we don't have the necessary information because it's a copy of the IFC file. So we start editing the information during the building process. And all this process is over, we can transfer this information back to the IFC model. So now we have the same information that we had in the web platform. And now our IFC file is an information compendium as ISO 19650 stands. Here there's a video as everything worked together. So we are starting informing the IFC class that we will work. And after that, we will use the web platform to generate our user personal token. So the user will have to inform username and password, and it will generate their personal token. And here we use this token to insert in the add-on to start to perform the operations. So here I'm pasting, and after that I will inform the URL address. Now we are ready to start to use the add-on. So let's create our first asset. So I just need to select an asset or object in my model and click in the create asset. And the information will be registered in the web platform. Now in this situation, the information is ready, verified, and audited in the web platform, and I want to transfer it back to my IFC file. So here we can see the information is done. So I will select the object and click in Receive Information, and I will send it to my model. We can see in the side model, I don't have the information. When I refresh, now I have the information in the correct IFC class. I can do the same in the opposite direction. Now I want to update the information directly on Blender. So I will change the information to 10,000 BTUs for 50,000 BTUs. I add it in Blender, and after that, send information. I will update my database. And for last one, the bulk creation operation. So I just need to inform my FC class and click the create asset. And with it, all the information will be registered in the web platform just with one click. As conclusion, the component number 1 was able to provide an initial guide to help the owners to drafting their asset information requirement. The web platform was able to organize and centralize in the friendly environment for auditing the information. The API ensured a bidirectional flow of information between the database and the add-on. And the add-on correctly allocates the information in the IFC schema using the BIM model as a centralized data repository. And for last, all the entire workflow relied exclusively open tools and open BIM solutions to prepare the model for the operational phase. Thank you for attention. Obrigado.
Thank you. You can stay here because you were the last one. If I could invite the first 2 presenters or groups of presenters back to the front. You can just stand somewhere in the middle here is fine. Okay, so first question.
Thank you for your presentations. My question is for the CarbonSmart group. I was wondering, where do you get the database for your embodied carbon and ensure the accuracy representing the projects that you work on?
Who would like to?
Yeah, so as we mentioned, the context for our project is based in Singapore. So for the database, actually for Singapore under the Build Construction Authority, there's already an existing one where it lists out all the materials, embodied carbon values are all there. So in order to integrate and properly use it for future in Singapore, we actually follow them and use their guidelines. Yeah.
This is a question for each of you. In each case, what do you do with information that's either not in the BIM or is, in the case of scan-to-BIM, is HVAC material? In the case of carbon calculator, what about HVAC objects? So I'd like to get a feel for what the scope of your 3 projects are in terms of what they can't do.
Who would like to go first? Yep.
You want to know if the information is not in the BIM model. So in this case, the information is not in BIM model already. So the information is not there. So for this case, we analyze the information, the asset information that we wanted to work, and it was set in the database, in the website database. Because I did it, because I understand in this phase, most of the users doesn't understand the IFC schema. So the information requirement was set. It could be opened for work with others information requirements. But for that, the user must inform the correctly IFC property set. And I think it's not the people It's not ready for it yet. So I could do it, but in this, for now, not. And so this is the way I prefer to work.
Who would like to take it next? Yep.
Thank you so much for your question. As for your question for those information not in the BIM, so actually we have some of this. As for our evaluation for the user IFC model produced by user scan-to-BIM algorithms, so many of those user IFC model does not contain information like IFC space. But one of our metric is about the topological metric, which evaluate the topological accuracy of these models. So basically, what we do is we extract the topological information from IFC model based on the geometry. So to be more precise, we evaluate whether we calculate whether the room or whether the wall components and also the ceiling and also the slab, whether it is enclosed. So it is very certain. It is certain, not like the IFC space. If they do not provide us with that kind of information, it will be hard for us to evaluate. Yes.
Yeah, so I think for us, the gap that we tried to fill was with the AI material substitution, in that because our scope is focusing on the pre-construction design stage, sometimes our materials are not defined. But we're basing on the assumption that with the ecosystem of models being submitted into the Singapore platform, we can train the model and learn from the past models to recognize, what potential materials can be filled in. And I think we also acknowledge that embodied carbon documentation is never 100% accurate. It's impossible to get every single thing right. But what we try to do is to get a better estimation of what is included in the BIM model. I think even in the normal process, consultants often also assume some calculations, assume some systems. Yeah, so I think for us, we see it as a better estimation of what the current process is. Yep.
Thank you very much. Can probably afford 2 more minutes if there is a burning question.
So, congrats, the three of you. You are the final one. So your names will be forever in the openBIM Awards in 2025. Congrats, it's incredible. And all of you have presented pilot cases, examples, but I will want a short word about the practical application of your work on the market, on the industry. Some of you have already prizes and publications, and all of you presented pilots, so that I know. But how can you foresee, what's your vision for the work of each one of you? I want 2 or 3 phrases or words for you to explain how can you have practicality in what you developed.
Yeah, please.
So in our case in Brazilian Army, we don't have a lot of engineers. So, and we lost a lot of time doing the same work several times, repeating the same task. So the solution that was developed is helping us avoid it. So we expect that we don't need to regenerate all the information again to prepare the model to start the operational phase. So we can save time, save people, save money. So
I think for us, we know that the process of designing a building is not easy. It's complex. You do through many revisions, and if a client says to change something, it has to go through every single team. Everything has to be updated. So I think for us, the practical part of our solution is that with all these design changes, you can still consider embodied carbon. It doesn't need to be like that your model is updated, then you need to tell your specialist, oh, this has been updated, they need to check this, check that. For us, we try to really simplify that process and reduce those kind of annoyances, I guess, that we see in the industry. Yeah. Yeah.
Yeah, thank you for your question. So as for us, we believe, to make it short, data is the foundation of technologies. So that is what we believe. So as for no matter we in 2D or 3D or scan-to-BIM, so those AI technologies, they really relies on data. And also annotating data is a very time-consuming and very time-consuming job. So as for us, we believe that releasing our data as open source can help them to reduce the cost. And also, we build open source community around our BIMNet, aiming at providing more collaborations between researchers and to fuel more applications to AI plus AEC. Yeah. Thank you.
Thank you all very much. Please be reseated, and we will start with the category of professional research. So, to get things underway, if I could please ask Strategic Building Innovation to the stage. Thanks.
All right, good afternoon. We are Strategic Building Innovation. I'm Calvin Cam. I've been in this professional research journey for 25 years and counting. I'm with Strategic Building Innovation as founder CEO and also Stanford University as an adjunct professor. Joining me here on my right, it's Amy. She's currently based here in Europe. And then we started working on research and education back 12 years ago at Stanford University. And joining me here on my left, it's Kayla. She also has joined my team's professional journey about 6 years ago. So why we're here? We want to focus on how can AI be a friend in the whole life cycle journey of carbon data management. We have seen that the problem is that it's tedious, it's difficult. We do get the results almost 12 months later on. The data mapping may be inaccurate. So our team focuses on how AI can help or not, and how to not only work with openBIM, but to even bring utility information, utility bill, paper into the openBIM workflow. So like any research, it's important to understand the stakeholders. And in our case, both academia and also professionals, leading owners, operators across 3 continents. What we've heard from many of them in this journey is that it's taking a long time. If they do it, it's tedious. It's very difficult to get the right information in at the good time so that you can look earlier on into reducing embodied carbon. And we've also seen that not just by words of mouth. One of our Stanford University Sustainability Fellow, Yelani, she actually worked on hundreds of files and could quantify that only 6.5% of the data would be relevant. But the time to scout through all this information, it's taking long. And then across the Pacific Ocean with Hong Kong University of Science and Technology, to take one version of good life cycle analysis takes 6 to 12 months. A lot of painful waiting. Yes, the BIM is there, but then they cannot quite start the LCA process. And so, as we know, in this openBIM ecosystem journey, that we have lots of tools, but then they each have their own pros and cons, right? They each have their own way of doing things. But then to really get good carbon data, we need to also look at the end in mind, right? Different regions have different carbon emission factor, have different local ways of doing things. How do we localize? How do we work with different applications around the world? Those are what we have seen with our professional research. And again, we also, professional research, we also work with leading agencies. Like in Singapore, this is JTC, who is also the guardian of the Singapore Green Building Calculator. Fintei, the group director, has quantified that it takes months, weeks to actually come up with that workflow, even if they have the BIM in place. Of course, like in any professional research, we need to look into the body of knowledge. We can respect and highly appreciate that there's a long list of body of work into life cycle assessment. With native BIM, yes. openBIM, we're starting to see a lot of initial work in this area. There may be something about natural language processing, about inference, but then really very little about AI, artificial intelligence. That's where we want to come in. Our research question is, yes, we want to work with the openBIM workflow, but how do we augment AI to be a friend rather than just errors and omissions and random results? So our look into AI is divided into large language model and also vision language model. And with both, we can actually get the best of it to also then see how AI can be fed with American, with European, or with Singaporean local information that are different from one another, but let the retrieval augmented generation, let the knowledge base to do the job. And before you feed it to AI, we need to have good gateway, pre-processing, post-processing, data splitter. That's the augmentation we talk about to make AI be a friend of the openBIM family. And so in professional research, we also need to build on the best out there. We work with some of the tallest building in the world. We work with some of the best research. So, and I'm serving as an adjunct professor at Stanford University, my 25 years there now, 25 years there. And then some of our PhD research work has been looking into native BIM with AI, has been looking into vision language model or vision computer vision with traditional invoice. Now the opportunity is that how can we bring those body of work research into openBIM? So on the left-hand side, if we look into early stage, want to understand embodied carbon, our focus is that how we can use retrieval augmented generation to then let it be tuned, fed with local standards, local building code, local purchase order, delivery order. And of course, as you know, there's so many different forms of AI out there. So a research and development team look at what are the performance metrics? How do we go with which AI? Even different versions of the same AI can give you very different results. And then later stage, in terms of operational carbon, we still work globally with utility bills that may be on paper, that may be on different forms. How can we use AI to be a friend and turn those semi-digital information into the openBIM workflow? And similarly, how does a vision language model within AI can be augmented to make it work? So in the first use case about reducing embodied carbon, yes, our team has been working on IFC research, in my case, since 25 years ago. We've been looking into BSDD IDS research for 5 years ago. We are working with version 0.6 of IDS at that time at city scale. So we build on those body of knowledge in this research. But the key focus, as I mentioned, it's how we can feed the AI with local practice. American standard, Singaporean standards. They should be different in those different adaptations, and that's what the retrieval augmented generation is about. And so validation, it's important that it's valid and examples out there. So working with the Singapore government, JTC, they gave us 4 BIMs, and we were able to then bring it to the openBIM format. Our AI with the retrieval augmented generation that we talk about was able to then infer 1,815 material types that map to the Singapore Green Building calculation. Again, that's different from how you may do it in Europe and in US. And then in the end, our openBIM visualization can visualize based on embodied carbon. Again, the original BIM has missing, has error, has no information about those. And so it's also about not how we validated it, but how the government agency was able to tell us that, okay, it took them almost a month to complete that. Now we can reduce it down to hours. Even the first try. Imagine we can do it 5 times, 10 times later on. So, but at the same time, the variance to the traditional approach, and by the way, how good you know is the traditional approach, anybody's guess, but then we are within 94% of their traditional carbon calculation. And indeed, we also get the official recommendation by the group director herself, Finte, talking about this research and how this can support greater efficiency, reliability in the carbon practice, and how we can also show the potential to inspire our friends in Singapore. Now, let's move the validation to one of the tallest buildings in the world, this skyscraper project. We have been working with them. It has openBIM, but once again, there was no carbon calculation in mind, and let alone finding the engineers and the sustainability managers from 20 years ago. And so we were able to then change the RAG with the local practice and the local standard from Hong Kong and let the recommendation and the influence to take place. And the response is that you can see an openBIM platform, how we can read some of this information based on embodied carbon. And then we also want to move beyond embodied carbon to look into the operational stage. So Kayla, tell us more about that.
Thank you, Calvin. So beyond the embodied carbon calculation, we also tackle the operational carbon. We use the visual language models to read the utility bills, and then we use openBIM to visualize the data so that the performance insights will be more clear and actionable. This is our workflow. This is our workflow. So first, user uploads IFC file with the space objects. Our team is also exploring using BSDD and IDS to validate the data so that the result will be more ready for the analysis in the future. Second, user uploads utility bills, and our augmented visual language model will be able to extract the data like energy consumption, billing period, the cost from different types of utility bills and even from images. And then we also implemented the pre and post processor to ensure the outcome would be more consistent and accurate. And eventually we will map the results on the IFC space so that we know and calculate the energy use intensity. And the team can easily identify the areas where we can cut down the carbon emission and cut down the energy usage. We also implemented the workflow in the building just mentioned by Calvin, ICC, and there are around 700 of energies bill uploaded to this platform. And among all, the average processing time will be about 20 seconds per bill. And there's a 94% of time reduction compared with the traditional workflow. And more than that, now the team can easily see an all-in-one integrated dashboard of their performance from energy and waters, etc. Let's see Mr. Jeff Ng, the Senior Manager of ICC Property Management Team, about the outcome.
Uses this AI platform to extract data from 700 utility bills. Having process time by 5%, and analyzing greenhouse gas with multi-factors. Helping us achieve our sustainability goals.
So yes, really getting third-party validation on actual live project, it's an important part of our validation. And so in this case, yes, we have worked with 300 IFC files. We have worked on the operational stage. They have a CDE following ISO 19650 with information management. Yet the key addition here is to leverage vision language model and be able to turn utility bills, traditional paper ones, scan ones, photo ones, turn them into carbon data within seconds, and we can do batch of them. And then, in the end, let this utility bill on paper form be superimposed back into openBIM so that we can see the energy use intensity based on operational carbon in an IFC openBIM platform. And of course, we should do it on our very own building. So this is our own headquarters building in California. We are proud to have received LEED Platinum when it was completed a few years ago. And guess what? Exactly like those global examples, we turned 230 utility bills through our AI and then bring it back to the openBIM workflow. In short, we can handle that in 15 seconds per file, and we can do it in batch. And with this kind of research, we were able to propose it and got good support from agencies, government agencies, not only here in Europe. I was over at Molio and Delft TNO a few days ago, but with California Highway. Caltrans not only saw the promises, they actually team up with us, California Highway, to go after federal highway grants. And federal highway also gave us good report. And that also applied not only on the horizontal side with the GSA Public Building Service, first using openBIM 20 years ago. They also saw that the promise of AI for this automation for green-proofing ground was huge. But more importantly, it's also about this is only a step in this direction. Our research journey is still ongoing. Yes, we are looking at AI for operational carbon, AI for embodied carbon, AI for lifecycle management, and how the different parts of large language model, different versions of it, vision language model, how you do post and pre-processing, can be a part of the open BIM workflow. But more importantly, working with academia, working with industry leaders, it's about improving processing time, reducing cost, improving audit trail confidence, and make sure that the open BIM workflow works. And then with Amy, over the last year or so, what do you see how this may make sense, for example, here in Europe and also in the US?
Great, thanks. I'll just take us home with some industry insights. Having worked in the US and the EU as a sustainability consultant for small architecture firms, global AECO firms, it's very clear to me that there are growing pressures for these types of tools to do life cycle analysis, but the current tools are just very inadequate to do this in a timely, efficient manner to make sure that designs are augmented or that operations can be modified in time. So it's been really exciting over the last year and a half to kind of inform this professional research project with what I see in industry and see how AI can help solve this problem. There's been mounting pressure from regulations, corporate climate commitments, and also just client expectations. So being able to solve this problem will be of great value to the industry and help relieve those pressures and more importantly, enable some new leaders to emerge in this space. So thank you. That's it.
Thank you, SBI. And the next presenter is Carleton University from Canada.
Good afternoon, everyone. My name is Stephen Fye. I'm the director of SIMS, or the Carleton Immersive Media Studio. We're a research center at Carleton University in Ottawa, Canada. On average, we employ 40 people, ranging from undergraduate students to PhD students, as well as graduates and even a couple of seniors. We're committed to advancing digital transformation in heritage conservation, architectural rehabilitation, and asset management. And our work demonstrates the potential of academic and industry collaboration. The project we're talking about today, developed in partnership with the National Research Council and the Department of National Defense. My colleagues are sitting at the table. Project is titled an Integrated Open Source Digital Twin Platform for federal built assets in Canada. And this was developed by 8 individuals over the last 24 months, some students and some graduates. And this collaboration combines academic imagination with government resources and real-world operational demands. This project is a demonstration of the implementation of openBIM at a national scale with the intention of transforming how the Canadian government manages its infrastructure portfolio. Now, Canada faces a crisis of infrastructure information. For example, our partner, the Department of National Defense, manages approximately 21,000 assets located across approximately 100 million hectares. 100 million hectares. Canada's a big place. Spanning every province and territory. And these assets are both geographically and typologically diverse, from military bases in the Arctic to heritage buildings in the center of cities. And this massive portfolio is managed through fragmented information systems, siloed data practices, and incompatible proprietary technologies. And this isn't just a Canadian problem, it's a global challenge that openBIM principles are uniquely positioned to solve. So our response to our research question is fundamentally grounded in openBIM. And rather than offering another proprietary solution, we developed an open source, browser-based digital twin platform that places openBIM at its very core. Our platform architecture exemplifies openBIM's promise of interoperability. Built entirely on open source technologies, it federates diverse data sources into a unified browser-based environment. I'm going to turn it over to Laura.
So our project adopted a research methodology grounded in co-creation, stakeholder engagement, open standards implementation, and iterative prototyping. So there's two main components to our research. First, we conducted a comprehensive review of open and international standards for BIM and GIS. Next, we defined specific use cases spanning the full asset lifecycle from design and construction through operations and digital twin applications. We then identified the information requirements to ensure that the platform supports D&D's current operational needs while enabling future ISO 19650 compliance. This foundational work culminated in the development of EIR templates for D&D. In parallel, we defined the functional and technical requirements of the platform itself, and then through iterative prototyping, we used real-world D&D assets to test the integration of varied data sets into the platform.
Hello. So now let me walk you through our platform open source architecture. Starting from the top, at the user layer, the platform utilizes Next.js as its full-stack React framework. The front end uses Tailwind CSS and ShadCN components for responsive, accessible design across devices and languages. The platform integrates multiple open source libraries for the 3D viewers. MapLibre serves as our map renderer with Martin as its PostGIS vector tile server. 3JS is our main 3D graphic engine, while WebIFC from that open company powers our openBIM functionalities and native browser-based IFC parsing. Point cloud streaming and visualization relies on cloud-optimized point clouds, or COPC, handled through Poetry and Gyro 3D libraries. In the backend, Min.io provides object storage for binary files like IFC, models, CAD files, and point clouds, and all services are hosted in Canadian-based full-host infrastructure for data sovereignty. This architecture enables flexible deployment options that respect organizational security requirements. Large organizations like the Department of National Defense with existing IT infrastructure can download and deploy the entire platform on their own servers, maintaining complete control over sensitive data, while a smaller organization can securely access dedicated instances through browser-based authentication with data isolation, ensuring organizational privacy and confidentiality. This deployment flexibility ensures that openBIM principles extend from individual users to entire government departments.
So using Carleton as our demonstration environment for security purposes, I'm now going to walk you through the capabilities of the platform. So starting with our secure login, the authentication system assigns role-based credentials with differentiated permissions based on your organizational requirements. Once logged in, you'll notice our left-hand toolbar provides intuitive access to our federated data environment. We have our viewers, the map viewer, the BIM viewer, and the point cloud viewer, and then a database for sites, buildings, and files. This organization supports both micro-level building management and macro-level portfolio analytics. The toolbar also houses integrated tools, including NRC's openBIM LCA plugin, which uses IFC-based workflows for carbon benchmarking and automated model verification throughout a building's lifecycle. This integration demonstrates how our digital twin platform can create a unified, open standards-based ecosystem of analysis tools. All right, let's begin by exploring our site database. Here we can access comprehensive data for any site, including all associated buildings and files. Moving to our buildings database, you can see our advanced search and filtering capabilities. Users can search by year built, building type, and numerous other properties using standardized terminology. Drilling down to the individual buildings reveals comprehensive data tabs. We use the buildingSMART data dictionary to develop our properties, and our next development phase will research connecting these directly to the IFC models. Notice how we've integrated diverse file types. Here you have IFC, point clouds, documents, and multimedia, all accessible through the same interface. Now let me demonstrate what we consider to be our most significant technical challenge, which is the seamless integration of BIM and GIS. This addresses one of the central challenges we faced, which is bridging fundamentally different paradigms in a web environment. Watch as I add IFC models to our campus. Here we have 45 models totaling 4 gigabytes of data. Each model loads within sub 2-second performance, even for files exceeding 500 megabytes. Next, we'll add GIS infrastructure data showing campus tunnels, demonstrating how building scale and infrastructure scale information coexist within our integrated environment. This cross-scale integration required solving complex coordinate transformation challenges by extracting information from the IFC projected CRS entities and using the proj4 JavaScript library for accurate coordinate conversions. Users can also add comments and models directly to the map to share with other users, enhancing collaboration. Now, zooming out to Ottawa, I'm going to reveal our open data federation capabilities. The platform automatically retrieves open government data from different municipal, provincial, and federal sources. Here, we're adding neighborhood boundaries, Canadian airports, transit networks, and tax data. This integration happens through standardized APIs with no additional data manipulation required. We currently federate over 25 sources and counting. This makes previously inaccessible data sets easy to layer and visualize alongside your building and GIS information. The dynamic visualization controls allow for enhanced data and data analysis, transforming fragmented government data into actionable intelligence, supporting data-driven decision-making for all users.
Okay, now returning to the Carleton campus, let me now demonstrate the heart of our platform, openBIM standards in action. Opening this IFC model in our viewer showcases native browser-based IFC processing. The complete IFC structure is preserved exactly as authored, maintaining the entire IFC hierarchy. One of our major challenges was preserving complete semantic riches, property sets, quantity sets, material, and classification system while maintaining performance. This isn't simplified geometry. This is the full IFC schema accessible in any standard browser. Now, what will happen when I click on any building element? The Properties panel instantly displays all IFC attributes, entity property, measurements, material assignment, constraints, facing information, custom property sets defined during authoring, and more. Our platform supports multiple file formats. So here I am adding a DXF CAD file, providing additional reference information. We have created a three-dimensional editing tool for the user to scale, rotate, and place file in relation to the IFC. The user can also upload 3D models from various file formats such as GLTF, FBX, OBJ, among others. This multi-format capability ensures compatibility with diverse workflows, such as point clouds, while maintaining openBIM as the central data foundation. The integrated analysis tools work directly on IFC geometry. Our sectioning tool allows dynamic model exploration, while our measurement tool provides precise dimension and analysis. The user can add comments to enhance collaboration within our BIM viewer, but the platform also provides a robust implementation of the BIM collaboration format, or BCF, a cornerstone of open BIM workflows. By creating or importing BCF files, the platform enables structured, model-based collaboration. Each BCF topic is connected to a precise viewpoint within the IFC, moving beyond free text comments to deliver context-rich communication. Exploring these topics reveals the complete BCF lifecycle: identification, responsible party assignments, proposed resolution, and clearly defined status progression. This vendor-neutral standard ensures that collaboration data remains interoperable and accessible across all authoring tools and platforms. The platform also supports information delivery specification, or IDS integration, another fundamental openBIM standard. By importing IDS files, user can check IFC models against explicit machine-readable exchange requirements that define what information must be delivered and in what form. The viewer graphically highlights which model elements conform or do not conform to the specified requirements, making compliance checking both transparent and actionable during coordination.
So throughout the project, we've overcome significant technical challenges that we believe will advance the entire openBIM ecosystem. A few examples of the BIM GIS integration include, just to reiterate, solving coordinate system integration between IFC and GIS data paradigms, achieving enterprise scale performance for browser-based IFC processing while preserving complete semantic richness across web platforms, and imagining BSF implementation at an urban scale. Our roadmap for development includes the integration of artificial intelligence, large language model technologies to enhance data analysis, real-time operation sensor data streams, and global search and query capabilities across data sets. The beta release is scheduled for this fall, 2025, and will make the core technology of our platform accessible to the broader community. By open sourcing our research, we are ensuring that other organizations, hopefully some of you, can build upon our work and advance openBIM adoption globally. The future of the platform will be entrusted to a registered not-for-profit. Thank you for the opportunity to share this work. I'd like to introduce my colleagues. Lara Chow is the Associate Director of SIMS. She's been with us for about 12 years, 10 of those as Associate Director. And Nico Arellano is a PhD student who is just waiting for me to finish his revisions. Thank you very much for your attention.
Many thanks. And the final presenter of this category and of the day, in fact, is Alex Mitchell from HDR.
Hello, everybody. My name is Alexa Mitchell, and I am with HDR. We are an AEC firm in the United States, in Canada, and Australia. And I am representing the team. Can you start the slides? And I am representing the team that developed and is working on the application of these national BIM for bridges and structures. openBIM standards is a national standard. And I am also the principal investigator for the project. With me, I have Joe Brenner, and he is the lead bridge engineer on one of the projects that we are testing the standards today. So I'm going to talk about the project at large, and he's going to give you some of the details on how the standards are being applied to the projects. So let's start with the beginning. And what is the project, right? So this is an effort that brings over 20 state DOTs and the Federal Highway Administration together to put the resources to fund the development and the application of these standards at the national level so that every state has the opportunity to deliver projects in a similar way. So we are wanting these standards to be adopted, deployed, and maintained by the state transportation agencies, implemented by all the technology providers that we do business with today, and accepted by the industry so that we can encourage use and drive innovation. Because today, the way that we do business in the US is that contractually designed teams are asked to deliver projects using proprietary software, and we do not have the choice to choose what software we use, okay? So this is a big deal. So what did we develop as the standards? We follow the ISO process. So we developed an information delivery manual that tells the engineer what they should model for their bridges, an information delivery specification so that they can be used to check the compliance with the requirements, content for the BSDD, and is currently the US Bridge Data Dictionary under preview in the BSDD. You can find it today. And some documentation of the US Bridge spatial hierarchy and other technical guidance that we provided to the project teams that are testing the standards, and also provided to the software companies that are helping us deliver those projects. So the next step was to find bridge owners that were willing to test the standards, because up to this point, the standards were very theoretical. And so we have found 2 bridge owners, the Pennsylvania Department of Transportation and the Iowa Department of Transportation, to find real projects that are going to construction to test the standards. They both got federal grants from the Federal Highway Administration to fund the effort to specifically, number 1, develop a 3D model and whatever software of choice the team has. As part of that, establish and document the openBIM workflows that are being used on each project, with the purpose of advertising these IFC data files for construction. And in one of the cases, the IFC file is a contractual deliverable with minimal to no plans. This will allow us to enable construction teams to use those files. We are going to work with them through the process to use the files. And as part of that, we are developing training and sharing best practices with the community at large, not only in the US, but internationally. These projects are very simple projects. They are bridge replacements, meaning that we remove an existing bridge and we put a totally new bridge with minimal road work. And the use cases that we are testing are quantity takeoffs, design authoring, design reviews, digital layout, BIM to feel, and owner approval, if you consider that a use case. So what this slide shows is some of the metrics that we were able to capture through the projects. We prepared 3 different projects, 3 different approaches, but what this demonstrates is that each team was able to produce thousands of objects in an IFC file, and multiple IFC files. The scope of these projects are very similar, but the teams are very different, with different knowledge of BIM, different knowledge of openBIM, working together collaboratively across state lines. The research project, the standards that we developed, provided a very high level overview of the digital workflow that we had in mind for these standards. Number one, starting with, okay, you choose the software of your choice to develop and author your model. Then you use the software to add the information requirements, to append the information. And I like to know that sometimes this requires special configuration of your software. It doesn't come out of the box. You're gonna have to do some work. The next step is to modify them as needed, because if they come out of the software as element proxies, that's not gonna be helpful. So we went ahead and modified so that we could create a file that would eventually pass the validation service. And so we are confident that these files are of good quality. And then we took the IFC files that were validated and run them against the IDS to verify the compliance with information requirements, and ultimately delivering a quality file for the construction team to use. And I'm gonna pass it on to Joe, who's gonna give you more details.
All right, thanks, Alexa. So here's our software map. This is a little larger and more complex than we originally imagined when we started this process, but I think it really shows the benefit of the openBIM process and standardization. So one thing you'll notice here is this is for all 3 pilot projects, and all 3 took a slightly different approach in order to deliver their design to construction IFC model. All right. 2 of the projects use the same vendor for both their bridge elements, solid elements, as well as their reinforcement. Same vendor in their tool suite. The other project was the SR6 project for PennDOT, which Michael Baker was the lead designer for. And we actually went with 2 different vendors, one for the solid elements and one for reinforcement. And the reason for this is that was one of our objectives, as Alexa mentioned, was to have a contractual deliverable for an IFC file for the bridge. So there was no proprietary bridge file formats delivered with the project. That was now bid and hopefully awarded here very shortly. And with that, the other projects, and with that, we had a very strict timeline in order to complete this. So we needed a authoring software, model authoring software that was able to give us a clean IFC file through the QA/QC process as we were turning around very quickly the milestones of this project. So again, I think this shows openBIM at its best. We could not have done it just with a proprietary format. We had to use 2 different vendors in order to deliver that IFC file. The other two projects, as Alexa mentioned, had some modifications with Bonsai and Quadri manual manipulations. But at the end of the day, all three projects were validated through the BSI validation service and IDS. And now as we go into construction, both PennDOT projects are in the bidding phase and one has been awarded. Now the contractor has the ability to use the IFC federated model in whatever software they choose. As far as properties, we started with everything we could from IFC, right? The property sets, attributes, properties, using the IFC as our base. And on top of that, the pooled fund had put together an IDM, had published an IDM with different property sets for the bridge elements. So this basically builds on top of the overall IFC schema. And you can see the format there in the BSDD that was developed for US Bridge. Moving on, there's also custom property sets. In this particular case, PennDOT already had developed sets for other digital delivery projects, not necessarily openBIM, but we had our own specific PA Bridge software property sets that were now being delivered. And what we're doing now is comparing those custom property sets to the overall US Bridge data dictionary and property sets to look at, okay, where are some of these gaps? Do we need to maybe move this property to the national standard, or is this something that is just for PennDOT's custom use? And that is very important to the research and moving forward for lessons learned, as each state is going to have some specific customizations that are needed, and we can figure that out, and we've worked through that process here as part of these pilot projects. Now I'm going to turn it over to Alexa to wrap us up.
Thanks, Joe. All right, so you heard there's a lot of work that has happened over the last 6-7 years in the development of the standards. We went from starting, when we started the project, we had a different methodology of openBIM, and then throughout the project, we switched to the IDS methodology. So we had to change our methodology there. But in the end, we do have some really great outcomes from this project. Number one, the project itself, the project teams themselves benefited from the standards because they had something to go by. It wasn't a one-off, right? Like, it wasn't just for that project. This is something that 50 state DOTs and 4 territories agreed upon. That's huge. In my lifetime, I've never been present where 50 DOTs and 4 territories agreed on something. But they did on this because resources are scarce and they know that there is value in this. This is going to be a huge impact. So the project teams benefited from the fact that they could choose whatever software they wanted to deliver the project, because they should be concentrated on the design and not the tools. So we proved that even though a lot of the software is not quite out of the box ready, we can make it work. At the national level, we demonstrated that when we come together and we set our mind, we can develop national standards that are going to provide the consistency, repeatability, reproducibility, so that every state can properly produce IFC files with the proper guidance. We now have documentation of these workflows. We now have lessons learned to improve the standards that we developed, to make them more practical, and training. And this is all at the national level, but we all benefit from it because we are in the process of figuring out how to share that at large. There are some things that we learned, right? And as engineers, or at least in the US, as engineers, we're not really IFC experts. So it was really important to start with an education component of what the IFC process is. That was very important. And the other thing that we found is that examples of how it has been done before are very important. And we did not have any of those, right? And so now we feel very confident that we can share those examples to help other people. And I'm going to close this out because with an acknowledgement to our project sponsors. These are the 23 states participating plus the Federal Highway Administration funding the overall, what we call a transportation pooled fund. They put their money together for a common goal to fund the project. The BIM for Bridges and Structure Executive Committee owner members are there listed, and unfortunately none of them could be here today, but they're very excited about the progress. And the 2 state DOTs who received funding from the Federal Highway Administration to help us apply and implement the standards. Today you only saw Joe and I, but we're a large team. And I like to show this because in the US, we say it takes a village, and it really takes a village. We had people that developed the standards. We had people that did coordination at the state level. We had BSI help us with an accelerated program project. And we really believe that through this project, we're going to accelerate the adoption of IFC and openBIM in the US, because we not only tried IFC, but we tried IDS, IDM, the BSDD. And so we are really learning and accelerating our adoption. And with that, I thank you for your attention.
You can stay here. Okay, if I could ask the first 2 groups of presenters to come back up to the front. And we are at time, but we will of course still do a question, probably a question each to each submitter. Who'd like?
Could each of the excellent teams just say something about what they see as the novelty of what they've done, and what the significance of that novelty is?
Okay, so same question to each of the 3 teams. Who would like to take it first? That was equal timing. We'll go with Alexa.
I would say that the novelty is it had never been done before, right? The open national standards at this level, right? We couldn't find examples, right? But I know that there are some, but these are very specific to, like, I like to say, this is equivalent to if you were able to get an EU standard. Every country in the EU agreeing to something, because that's the equivalency of that. The impact really is, 5 years ago, nobody knew what the US was doing on openBIM. We didn't exist. The impact is that we are accelerating and really leaping, just over our own knowledge, really. 5-6 years is really not a long time to go from not knowing to leading some work and working with our international community to learn more from each other. Anything else?
Yeah, I would just say even to build on that, the practical application for workhorse type structures we like to call in the US, not just the one-off, cable stay signature structures, but things that we have thousands within the US.
All right. A case, I think it's how to let AI work with openBIM. How AI actually allow us to be a little bit more forgiving. We can now work with BIMs that may not have all the materials, and AI can be fed with local information and make that inference. How we may traditionally have utility builds that are not in openBIM, and we can let vision language model to bring them in. So.
Yeah, and I would say it's just kind of the perfect application of AI, of taking something that's super manual and super, you have to sift through many papers or Excel spreadsheets to get the right answer. And this is, applying AI in a way that you can take something that takes weeks and now it takes hours.
So for us, I'd say that with our solution, we want to democratize digital twin technologies. The complete solution is open source, no proprietary components to it. And I think this allows many other organizations, researchers to actually build on top of our platform powerful analysis tools that other organizations can use. And for us, a big concern is data sovereignty. So for us, we have complete control over the data using a Canadian-based cloud service, but also for organizations to be able to download it on their own infrastructure, you have your own data security.
Excellent. Thank you very much. And with that, we have a wrap. So thank you to everyone who's joined us for this session and everyone else who's joined us in the previous sessions today. Jury will now go and deliberate to determine the final 2 winners, and we will announce everything tomorrow in the closing plenary. Thank you again.